This recording is for the normal distribution, part 1. The normal distribution is a continuous probability distribution, unlike the binomial, which is a discrete. It's widely used since many data sets are normally distributed. The graph of the normal distribution is called the normal curve, which here's a small picture of it up here in the corner. We'll see several more as we go. This also relates to what we've learned in the past regarding the empirical rule for bell-shaped distributions. So this normal curve is that bell-shaped distribution. Here are some properties. The mean, median, and mode are equal. The normal curve is bell-shaped and symmetric about the mean. And the total area under the curve is equal to 1. And the normal curve approaches but never actually touches the x-axis as it extends farther away from the mean. Now, the reason why we care about area, why would we care about how much area is under that curve, is because area is going to be the same as probability. They're going to be equivalent. So when we're finding area under this curve, we are actually finding probability. Now, this graph I have down below is just basically a graph similar to what we learned with the empirical rule. It just has it sectioned off with the mean in the middle and plus and minus 1, 2, and 3 standard deviations, which we're going to get a lot more detail than just plus 1, 2, and 3 in this lecture. And so you see the percentages a little more specific than they were before. 68 for the empirical before, now it's showing you 68.2 is a little more accurate, 95.4 and 99.7. Now the graph on the right is just kind of showing you that while the graph will always be symmetric, the mean in the middle, the total area will always be 1, it can have slightly different shapes, and what causes the change in shape is the standard deviation. If the standard deviation is small, you will have a taller and narrower graph because more values will be nearer the mean. On the contrast to that is the larger standard deviation will make a graph be more spread out and flatter because more data values will be farther away from the mean. But either way, both those graphs in this picture on the right would have a total area of 1 unit if you smash them into 1 square unit. On the right here, we actually have the equation for that graphs the normal curve based on the mean and standard deviation, but it's pretty unlikely you would ever have to actually use this equation for anything. It looks pretty scary. It's got a pi in there, and it's got an e and several other things. But I just wanted to show you that, that there is actually an equation that generates this graph. There has to be. But fortunately, we're not going to have much use for it. Let's look at this example. Now, these 3 graphs, which I drew a red line in the middle representing the mean, which of the 3 graphs would have the greatest mean? Now notice the mean is basically being displayed on the x-axis. So in this case, the graph that's farther to the right would have the largest mean because it's a larger x value. So we have a mean of 60 for graph B, it would be the largest mean. The other 2 look like it's about 45 is the mean. And which one has the greater standard deviation? The greater standard deviation will be the flattest graph. So that would be graph C. So therefore, had they asked which one has the smallest standard deviation, that would be graph A, because it's taller and narrower. Now, you probably would have no need to do what I just did in this example, but I just took a TI-84 calculator and used that ugly equation I showed you up there with the same 2 means, because I want them to be lined up with the same mean in the center with 2 different standard deviations. So I just manually typed in the equations here, and I had to play with the scale to graph these a little bit. A normal scale would not show them very well. But with mean 5, standard deviation 5 and standard deviation 10, based on what I was saying before, the one with the smaller standard deviation should always be the taller and skinnier graph, which it was here. Y1 is definitely that taller graph, and then Y2 is the flatter graph. But I doubt that you're going to have any serious need to ever have to do that. Now, when we calculate probabilities in a normal distribution, they're going to always be expressed as inequalities. And in fact, for any continuous distribution, which there are others besides the normal, but we're not studying those in this class, the probability that the random variable would ever actually equal a specific number is 0. We have to treat them as less thans, greater thans, between two numbers, so we can calculate areas. Now, the common inequalities, like I said, would be less than, greater than, and between two numbers. Now, notice what I have written here in red. For a continuous distribution, which is what the normal distribution is, it really doesn't matter whether it's less than or equal to or less than. Same thing with greater than or equal to or greater than, and then between two values. It wouldn't matter whether the equal's there or not. The reason why is because being continuous, the values for x are continuously moving on a number line. So as I mentioned over here in this box, for a continuous distribution, the probability of x less than 3 could theoretically be 2.99999. In other words, the area would go all the way up to 3 without touching it, but it would be so close that it would essentially be the same thing as if it would have touched the 3. Now note, this is certainly not true in any discrete distribution, including the binomial distribution. There's a huge difference between less than and less than or equal to. But in a normal distribution, there is absolutely no difference whether you have the equal there below it or not. So, for example, greater than 2 or greater than or equal to 2 would be the exact same calculation. Now here's an example. So for a discrete distribution, if you were between 12 and 14 without the equals, that would only be 13. But like I'd used a binomial as an example, but technically that's could be for any discrete. 12, 14 inclusive for binomial would be 12, 13, and 14 added together. But in the normal distribution, between 12 and 14 with and without the equals is absolutely no difference. None whatsoever. And I just kind of drew a little sketch here, which we'll see more of these later. Let's assume that the mean of this graph was 10, so I kind of put 12 and 14 on the x-axis and shaded that. So essentially, that would be the area that would represent the probability that your x is between 12 and 14. Now, similar to the binomial situation where we had a binomial table, we had for different values of n and different values of p, but there's no table that can cover everything. And that's also true for the normal. It's, I just wrote some examples here of normal distributions that could be, mean 60, standard deviation 12, mean 120, standard deviation 30, mean 250, standard deviation 50. I could go on and on and on. And these are based on being random variable x. But we do have a nice way to convert any normal distribution to one specific normal distribution, for which we will have a chart to look up probability areas and probabilities. It is called the standard normal distribution, and its random variable is always z. So we will be converting any x distribution to a z. The standard normal distribution always has mean 0 and standard deviation 1. And in fact, we look over here to the right, that formula is the same formula we used to find z-scores before. It is the same formula. So z equals x minus mu over sigma. So the way you calculate your value, z, you just take your x value, you subtract the mean, and you divide by the standard deviation. So here's an example where I say, all right, we're going to convert a couple of values of x. One is 60, one is 32, from a normal distribution that has a mean 48 and standard deviation 8 to a value for z. In other words, the standard normal distribution. So I took first one, I took 60 minus 48, divided by 8 gives me 1.5. 32 minus 48 divided by 8 gives me negative 2. So we've calculated both of those x values to appropriate z values. So what I have written here, essentially the z measures the number of standard deviations that the x value is above the mean. So for the last example, 1.5 indicates that that particular x value is 1.5 standard deviations above the mean, and negative 2 means the value is 2 standard deviations below the mean. Now let's start getting used to this standard normal table that we will be using to find our areas and probabilities. Now the standard normal table, which represents the cumulative area left of z, the table is only based on values left of z. So if we want right of z or between two values, I'm going to show you how to manipulate it to make it fit our needs. But the table itself is always left. Now, one thing to keep in mind is that your area, your probabilities, remember a probability always has to be between 0 and 1, which means these areas have to always be between 0 and 1. So your z-score can be negative, but your area and your probability can never be negative. So on our chart, we're going to have values you'll see right here where it's less than positive numbers and then less than negative numbers. So I have it where it's located in your book on charts and tables. Probably a good idea to print one out when you're practicing problems, or you can just look at it online. You will be provided with a new one to use for the exam. You don't have to bring that with you. Now let's look at this table, and I'll come back to these questions. I'll bring up the whole table here. So you can see here on the left side, those are your z values going down up to 1 decimal place. So it starts out at negative 3.4, and we come over the positive side and it has up to 3.4 here. So you go down that first column to where you find up to your first decimal place. Across the top row, that represents your second decimal place. So you combine the column you want with the row, and the row just adds in the second decimal. So if I wanted to find negative 2.64, I would identify the negative 2.6 row, which I've done over here to the left, and then I would go to the 0.04 column, and there it is, 0.0041. So let's look at these two examples that I have here. Find the area to the left of a z-score of negative 2.19. So I have the chart right here, so we can just use that. You can zoom in this a little bit. I just have the little snippet of the chart out that we need just for this problem. So you see over here, I've circled, it's going to be the negative 2.1 row, and then over here we have the 0.09 column. So the negative 2.1 meets the 0.09, and then we have a 0.0143. And that would be the area left of negative 2.19 on the curve. Now how about positive 2.17? Let's see what that's all about. So over here, I sort of had to kind of splice the table because I wanted to show the top row. Otherwise, it would have been too much to copy. So you normally obviously won't have this gap between the 0.4 and the 2.0. So we have 2.1 row and the 0.07 column. So you put those together, that makes 2.17, and I have circled right here 9850. So that means the area left of 2.17, here's the answer, 0.9850. Now you can also come up with these areas using the TI-83 or 84 calculator. There is a function that is in the same general area where the binom PDF is. I have the keystrokes listed right here. I will type one in just so you can see, but there are the keystrokes, how to get to it. But the way you have to enter it is the normal CDF, you have to put in the smaller value and then the larger value. So for example, using the ones that we just did for less than, we would have to treat the smaller value as negative infinity. Remember, interval notation from algebra, like if you had less than 6, that would represent negative infinity to 6. Or if you had greater than 9, that would be from 9, positive infinity. So interval notation from algebra. That's what the calculator wants. Now I put in negative 100. Now in real numbers that doesn't sound like it's very small. I'm using that to represent negative infinity. That doesn't sound, you would think you might need a number with negative and a bunch of more numbers to it. Like negative 10 million or 100 million. But on the normal curve, negative 100 is pretty far out there because it's the concept of the fact that 99.7% of your curve is between -3 and +3 standard deviations. So negative 100, a z-value of negative 100, is way far out there. This graph never actually touches the x-axis, but it gets so infinitely close it might as well touch it. So that's, on the normal curve, negative 100 is out there. I think negative 10 would even get the job done. If you wanted to use negative 10, that's probably sufficient. But I use negative 100. And with interval notation, if you're using negative infinity, it must go first. So negative 100, negative 2.9, I'll actually type that in there. So I go second, there's distribution. So the binom PDF that we've seen before for the binomial distribution, that's a little farther down the page. They made this one close to the top. Now you don't want to use normal PDF here. You always want to use normal CDF. Do not use PDF. So I'm going to put negative 100, negative 2.19. Enter. 0.0143. Rounded to 4 decimal places. And you look up here, and that was the value we got right here. That was the chart value, 0.0143. So that worked just fine. So you can do it that way too if you like. Now notice for the next one, it's also less than. So we started at negative 100, but I put in positive 2.17 as my upper value. So it's a lower value, upper value. 0.9850. Now let's suppose I just did this. Go second. Clear this. Clear. And I'll just go. Suppose I went negative 100 to 100. See what happens. It's 1. And that basically is the same thing as one of the definitions on the first page about the properties of the normal curve. The total area under the curve is 1. So I was expecting that to be 1 as the answer. All right. Let's scroll down here. Finding other areas under the normal curve. So suppose we have a problem that involves greater than, a probability that's greater than something, or at least. Remember, those are the same for a normal distribution. Area right of Z. There are 2 ways you can calculate this. One of them is you can look up the table value at your z, regardless of whether it's positive or negative, and then take 1 minus that. Now, why 1 minus? Well, the reason for that is because the total area under the curve is 1. So in other words, let's look at this positive one, for example. If you look up on this positive z, you look up the z, you're going to get the area in the open, the white region to the left of z. That's not what we want. We want the red. But since the total area under the curve is 1, the white area plus the red area would equal 1. Therefore, if you want the red area and your chart gives you the white area, 1 minus that value of the white area would give you the red area. So that's why the 1 minus would work. Now, the other way to do this, which is generally the way that I like to do it, but I'll indicate to students that since there's 2 perfectly valid ways to do it, you can pick whichever one you like. Now, I'm going to use the symmetric property of the normal curve. Since this graph is symmetric, if you flip it over, it's going to be exactly the same as it is on the other side. And look at these pictures down here. The area right of a positive z would be exactly equivalent to the area left of negative z. So you see the picture I have down here for number 1, how it flips over? Flip it over, and they would be the exact same. Well, why would I want to flip that over to the area left? Well, that's a good question, because anytime I have something written as area left, that will be the exact value on the chart. I don't have to do the 1 minus. If I translate this to area left, I do not need to do 1 minus. Same thing over here. The area right of a negative z is equivalent to the area of the left of that positive z by symmetry. So all you have to do is, if it's area right of a positive z, you can just look up the negative z value on the chart, and that will be your answer. If it's area right of negative z, look up positive z on the chart, and that will give you the answer. This is only for area to the right do you do this. If your problem's already area left, like we just learned before, then you don't have to do anything. If area left is already what the chart value is. So here's one where I'm saying find the area right of z equals negative 2.07 using both methods. So if you want to think of area right just being 1 minus the chart value, that's perfectly fine. You can do that. We can go look up negative 2.07. And it'll be right there. 0.0192. I can go 1 minus that, and I'll have it, which is 9808. Now here's another thing that's helpful, I think. Sometimes you might want to draw a picture. A picture's not mandatory, but it can be helpful. Because by sketching this picture, area right of negative 2.07, because remember this is the standard normal, z's in the middle, you just look at that picture and you can tell that that area for sure is an answer bigger than 0.5. There's about 0.5, the mean's in the middle, so you have an area of 0.5 to the left of the mean, 0.5 to the right of the mean. So we have area 0.5 to each side. Well, that's definitely more than half of that graph. So in other words, if I was to make a mistake and just look up 0.0192, I could then look at my picture and go, wait a minute, that's too small of an answer, so I know that that can't be right. And sure enough, it isn't. 1 minus that is correct, though, 9.9808. Or, part B, you flip it over and change the sign. You change area right to area left. You change negative 2.07 to positive 2.07. So if I look up 2.07 directly on the chart, I don't have to do the 1 minus. down here, 2.07, and there it is, 9808. So once again, you do whichever way you prefer. I like just flipping it over and looking it up that way. Or you can even, here's the calculator method. Now the calculator, you don't have to flip anything. You just have to realize area right means on your first number will be this number, whether it's positive or negative, it doesn't matter. So I put in negative 2.07, my first number, comma 100, representing positive infinity. Kind of like I showed you earlier with the interval notation. So area right means you're starting at the smaller number going towards positive infinity. So negative 2.07, comma 100. And that looks like it's probably right to me. Just look at that. I think it's 9808, isn't it? All right. Now, the next case, area between two different z values. Now, this one's really nice. You don't have to worry about flipping anything, or even if you do the calculator, you don't have to do any kind of negative 100 or positive 100 to represent the infinities. All you have to do is you take the larger table value minus the smaller table value. Now, one thing to keep in mind here is that these are areas, these are probabilities. Make sure your answer, is positive. So if you put the wrong number first and you got negative, you could then realize it's positive. Once again, z's can be negative. Areas and probabilities must always be positive. The reason why it works this way between the two numbers is because, let's look at this example, this picture right here, and you were trying to find between the blue and the white. Well, if you look up the chart value of the right edge of the blue shading, look up that number in the chart, that's going to give you the blue plus that area to the white. It's going to give you that total area. And then if you look up the smaller number of the left edge of the blue shading of the chart, it's just going to give you the white. So basically, and if you subtract them, the blue plus the white minus the white would then leave the blue. So that's why that works. So here's one that's find the area under the normal curve between z equals negative 2.16 and negative 1.35. So I found the two values, negative 1.35. Let's go back up here. It'll be the sixth column. There we go. Z.0885. And then area left of negative 2.16. Right here would be 0.154. So once again, it has to be the larger minus the smaller. So 0.0885 minus 0.0154 gives you an area of 0.0731. So just take the larger one minus the smaller one. Answer has to be positive. Now the last portion of this is just rewriting these questions as probability questions. That's probability is the same thing as area. So finding the probability that z is less than 0.45 means you're looking up the area under the curve for 0.45. Area left on the chart, you would get 6736. So 0.45 be right here, 0.6736. So that probability is area. And then greater than negative 1.85, two ways to do it. You can do 1 minus the chart value at negative 1.85, which is 0.0322, you get 9678, or you can treat it as flipping it over and changing the sign. You change it from greater than to less than, which is the same thing as area right to area left. You change the sign. Reverse the arrow, change the sign to positive. 1.85, you look on the chart, it's going to be 9678. Now, area between negative 1.45 and 1.23. We look up the chart value, so I'm starting to assume that we're becoming proficient at least in how to read that chart. So I'll sort of take some liberties here on this. So you look up 1.23, you get 0.8907. You look up negative 1.45, you get 0.0735. You subtract the larger minus the smaller, you get 0.8172. Now here are these calculations I did here. I put them in normal CDF. The first one, the less than, it was from negative 100 to 0.45, which is 6736. Greater than negative 1.85, I just did negative 1.85 to 100, representing positive infinity. There's 9678. And it looks like I didn't do between the two. Actually, I used a command. I wouldn't worry about this too much. I just use this to show that there is a function in there that actually graphs the shading and does show you the area. I prefer the normal CDF, but shade norm from negative 1.45 to 1.23 shows the lower and upper. It kind of blocks it out, so I'm not sure if I really like that too much. But anyway, right there above it, it shows the area, slightly different, 8171, 8172. That's okay, but I would not worry about this shade norm thing. Don't worry about it if you don't understand that. I just knew that function was in the calculator, so I wanted to show you. So that concludes the lecture for the normal distribution, part 1.